Okay, just to start off, I wanted to say thanks to all the people that had returned work so far. I realise the Google Doc had some issues with it. I think from now on, what I'm going to do is stick with giving out a fairly straightforward written task at the end of a lesson. I think you will have been given out your timetables by the time I put this up. I'm lagging a little bit behind. I'm still trying to get up to speed with the filming and the editing and the splicing of all the videos together. Hopefully I'll be getting a little bit faster at it. I do seem to be chasing my tail a little bit at the moment. However, the work that was put in with the electron arrangements was really, really good. And today I will post up a little picture of the perfect way to answer. I think some of you, I'll highlight on the picture. Some of you were putting the electrons, I think you actually had it correctly, but you were putting them out in a linear fashion instead of pairing them up when they needed doubled. I think you were still pairing it up, but I'll highlight why you might drop a mark if you do it in a certain way. So I will put that up on Teams today. Apart from that, I want to say thanks for everybody who's getting involved and getting the work done and trying it. Admittedly, this is quite different, it's quite tricky. I'm certainly finding it a lot harder to think about how I'm going to teach and how I'm going to put things out, but I really do appreciate the fact that people are trying. And what we'll do is we will have hopefully 2 YouTube lessons a week, one on Monday, one on Wednesday, and you can finish the tasks that are given on the Tuesday and Thursday. I think you're being given a timetable out. I want you to know from my perspective that you can try and follow the timetable. It might give you a bit of routine, but there's no pressure from me to do the work that I set out at any particular time slot. Whatever works for you will be good. So with that said, we will move on to starting with our little lesson for today, which will cover the diatomic elements. We will talk about ionic bonding, and we will talk about how to name our different compounds, and that naming should allow you to basically take any compound that I give you in the task, and you will be able to name it, hopefully, by the end of this little video. So first of all, we've got to do the diatomic elements. So the diatomic comes as, I'll use an X for element, if I can, and there'll be 2 of them. So when, that wasn't particularly good actually, it'll be X2. Ooh, might redraw that on a piece of paper for you as well. So I'll try and squeeze it in. Oh, there's a pencil. This might be a little bit easier. X for any element that's diatomic, and they come as a pair, so they come as 2. So the diatomic elements, we always find them in nature as a pair, so bonded together. So our first one that's diatomic is hydrogen, and hydrogen comes as H2. So we're going to have a hydrogen atom, and it's going to always come covalently bonded to another hydrogen atom, and that's our first diatomic element. So H2 is our first diatomic. Then we've got nitrogen. Now, interestingly, what we're going to do, this is going to be actually part of the task, you're going to have to figure out how many bonds hold these 2 nitrogens together, which is quite interesting. So nitrogen is another diatomic. It's found as N2. Oxygen, found as O2, and that's why we say it's O2, is because it's diatomic and it always comes, one atom of oxygen always comes bonded to another. So hydrogen, nitrogen, oxygen, and all of the group 7 elements. So going right down, chlorine, fluorine, chlorine, bromine, iodine, and astenine. Astenine's quite a interesting one. It's actually radioactive and it's pretty rare, but it is part of group 7 and it is technically found, when we do find it, as a diatomic. So these are our diatomic elements. You do need to remember which ones are diatomic. It's group 7, oxygen, nitrogen and hydrogen is the best way to remember it. You can come up with a mnemonic if you like, but really just remembering that diatomics are found in, these atoms are found as pairs, and it's always hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine and astenine. Those are your diatomic elements. What we're going to do now is we are going to move on to talking about ionic bonding. So we will do some work on just regular old paper with that. Okay, so when we're talking about ionic bonding, we are really focusing in on the bonding between a metal ion and a non-metal ion. This way of speaking about ions is sometimes a little bit misinterpreted. If you've got an atom, what you've got is the number of electrons will be exactly the same as the number of protons in the nucleus. So an atom has no overall charge. When you move from having no charge to a charge, you start calling that thing an ion. And so what we're going to have and what we're going to see is a metal atom becoming an ion and then forming an ionic bond with what was a non-metal atom that also became an ion and helping that bond form. So when we're looking at ionic bonding, this is the type of bonding found between a metal ion, and that metal ion is going to have a positive charge because it's lost an electron, and a non-metal ion that has a negative charge. Now, what I want to do is actually show you how and why this works, and you can think about it quite clearly. It makes a lot of sense once you see it drawn out. So, lithium, and the nuclide notation for lithium is this. So we've got a mass number of 7 and an atomic number of 3. And if you remember from one of the previous lessons, that atomic number is the number of protons, the mass number is the protons plus the neutrons. So I can figure out from this that I've got 4 neutrons, because if I take 3 from 7, that takes away my protons, I'm left with 4 neutrons. Now, if this had, at the moment, this is for an atomic state lithium. So this is in its atomic state, it has no charge. So if I draw out the electron shells, or as somebody quite correctly pointed out earlier, eventually these might be called electron energy levels, but you can consider them shells for now. We've got 3 electrons, and the first 2 electrons will make up a full inner shell, and we've got 1 electron on the outer shell. Now, that 1 electron on the outer shell, it basically makes this unstable and it wants to lose that electron, or it wants to gain 7 electrons. So you got to think to yourself, what would actually be easier for this particular atom to do? Would it be easier for it to gain 7 electrons and have a full outer shell of 8, or would it be easier to lose 1 electron and go down to this full inner shell of 2? Well, it's simply easier to lose that single electron. Now, to keep things as simple as possible for the time being, we are going to use fluorine, and the nuclide notation for fluorine, we've got 9 protons and our mass number is 18, so that means we've got 9 neutrons as well. So if I draw out our fluorine, we've got those 2 inner electrons, and bearing in mind this is our non-metal here and this is our metal here, so we've got our full inner shell, but fluorine has 1, 2, 3, 4, 5, 6, 7 outer electrons. And so now we've got to kind of think, well, what would be easier for the fluorine to become stable with a full outer shell? Would it be easier for it to lose 7 electrons or for it to gain 1? And in this case, it's much easier for it to simply gain 1, and that'll mean that it has a full outer shell as well. So what we are going to see is this electron here is going to be lost from the lithium, and it is going to be gained here by the fluorine. And because it's been lost here, then we get a lithium ion. And because we've lost a negative charge and we've retained that 3 positive charge, we get an overall positive charge of 1. So if you think about it, we have 2 negative charges plus 3 positive charges. That's going to give us a charge of +1. And we get a charge here of +1. And that is now an ion. The opposite thing happens here. So we now actually have we have 10 negative charges and we have 9 positive charges. That equals a charge of -1, and we get a 1 negative charge, and this is now an ion of fluorine, and it's an ion because it has a charge. If it didn't have a charge, you'd call it an atom. If it's got a charge, you'd call it an ion. So now we have the lithium with a positive charge and the fluorine with a negative charge, and we are going to see what happens when we've got these 2 different charges, because as you know, if something's positively charged and something's negatively charged, they're going to want to move closer together. There's going to be a electrostatic force of attraction between that negative charge and that positive charge. Okay, so I've redrawn these, and these are technically no longer atoms. These are ions. Now there's a very specific reason why we call them ions. It's because now they carry a charge. If we look at the nuclide notation for fluorine, we've got 9 protons. However, we now have 10 electrons because one of those electrons that was on the lithium has jumped to the fluorine. So the charge is 1 negative. So that fluorine now has a negative charge. The lithium, on the other hand, has 3 protons but only 2 electrons. So this lithium ion has a charge of 1 positive. And if we've got a positively charged ion and a negatively charged ion, there's that attractive force between the 2 is our ionic bond, and that's what's going to form, I'll make that a wee capital so it makes a bit more sense, ionic bond, and that will hold these two ions together. That will happen. So this So it's very, very difficult to do this with just two ions. What's usually going to happen is we're going to have billions and billions and billions of these ions. And what we're going to get is we're going to get a system where we've got our lithium, which I'm going to make blue, and our fluorine, which I'm going to be really annoying, and make aqua blue. Just so you can barely tell the difference. Now, if I start off with a lithium there, what I'm going to find beside it is a fluorine, and then I'm going to find another lithium, and then I'm going to find another fluorine, and then down from this lithium, I'm going to find a fluorine. Then a lithium. Then a fluorine. Then a lithium. Another one here. Another one here. I'm jumping ahead a little bit because I know where they're going to go eventually. Now, what we've got is this is basically forming a crystal structure, and once things get slightly more back to normal, they might open Greggs again. And in Greggs, you might find something called a chicken lattice. Now, it's called a chicken lattice because it has that crossed striation of pastry over the top of it. So the lattice structure is really this idea here, and so that is what the pastry's put into on the top of that chicken lattice, and it's the exact same pattern that we get in our ionic lattice. So this will form a ionic lattice, and this is our ionic lattice here, and it is, if you just think about it, being in the same pattern as the pastry on your chicken lattice. That is perfectly reasonable way to think about this. So this was our ionic bond forming. We're losing an electron from the metal to the non-metal, and that's going to create a negative charge on the non-metal, a positive charge on the metal. That difference in charge is going to create a force of attraction, and that's our ionic bond. The formation of that ionic bond, when it happens with billions of these ions, will form an ionic lattice, and this will usually look like a crystal. So this will usually look like a crystal. Now, what we spoke about in terms of valency still applies in a way to our ionic bonding. Now, you don't get discrete molecules in an ionic compound. What I mean by that is if you've got a covalent compound, this is going to have a very specific size and shape. In this case, we've got our tetrahedral, and this is our methane, or our CH4. And it's got each molecule has one carbon atom and 4 hydrogen atoms, all bonded with covalent bonds. That is a singular thing, essentially. Now, for our ionic compounds, we basically have an up to infinite array of ions all together. So when we saw our lattice, we had this idea here that there were ions, and all of those ions were all just bunched beside each other. Now, I could keep drawing this into infinity, essentially, and you'll find that depending on the size of the crystal, you might have trillions and trillions and trillions of ions just continually spreading out. And so all you can really say in this example here, if we say that that was our lithium and that was our fluorine, that the ratio is 1 to 1. And that gives you this nice clear lattice structure, and that's what they're going to be asking you at National 5. However, the ratio of these ions is determined by the valency, and the valency is not necessarily going to be 1 and 1. So what we can do is, instead of using lithium that's in group 1, we can actually take magnesium, which is in group 2. Now, because it's in group 2, it's got a valency of 2. And we'll just stick with our fluorine still, and our valency there is 1. When we swap those numbers over, we will be told that our ratio of atoms is Mg, and that 1, which I'm not going to write because it's a 1, and F2. That means when I look at the crystal lattice for this compound here, I'm going to find that I have 1 magnesium ion for every 2 fluorine ions. Now, you're not going to have to visualize how that looks, quite frankly, and really the ionic lattice is what you want to have in your head. The point that I'd make here is that you still need to be able to do the valence swapping for these. You're not going to have to visualize this as a lattice structure. So this ionic lattice structure is the one that they're going to show you, and it'll be a 1 to 1 ratio. They're not going to show you one that's got a different ratio than that. It is really quite fascinating stuff, actually. I really enjoy the crystal lattice chemistry that you do later on. It's really interesting, and it's really good if you like visualizing things, and if you like imagining what particular things look like at the atomic structure. It's really interesting. However, where we've got this covalent molecule, even though we do still have a ratio of 1 to 4 hydrogens, this thing is a discrete unit, and we could have another one here, and this would be another methane molecule. But these are 2 separate things. They're not part of one giant crystal structure. So it's important that you kind of appreciate that fact. So this is just this is really just telling you, when you're swapping the valencies here, the ratio of one of your ions to the other ion that you've got. So you'll have your metal ion and your non-metal ion. Right, that's that bit. Okay, so it is worth noting before we begin this that chemistry and the study of chemistry has been around for a very long time, and it is split into lots of different disciplines like organic chemistry, crystal lattice chemistry. There's a whole bunch of different subsections that we've got, and the names of different compounds don't always follow this rule within a given discipline. For example, if you've got carbon and hydrogen, that's hydrogen carbide. However, if you've got one carbon and four hydrogens, that's very often going to be just called methane. And so the names that I'm giving here is using the classic system for basically just naming the compound with what elements we find in it. However, depending on what part of chemistry you're looking at, what book you pick up, even what country the book was published in, you will find the names change slightly. It's really important that you know that there is a vast system of naming in chemistry and organic chemistry. One of the main things that you learn is how to use a really interesting and fun naming system to figure out what to call an actual compound by its proper name, to give you information about the functional groups and the structure of it. However, this is just the bare bones basics of if you've got 2 or 3 atoms, how you can name that thing. So what we're going to do is we are going to take a few examples and we're going to name them. So really, this is the big note for this, and then we'll do a couple of examples. Okay, so first example is we are going to get an ionic bond forming between sodium and chlorine. That's because this is a metal and this is a non-metal. Now, the name for this is going to start with sodium because that is closer to the top left-hand corner of the periodic table than chlorine. And so sodium comes first, chlorine comes second. Now, I'm going to stop there and I'm going to change this to ide. So sodium chloride, that ide really just means that only this atom there is no additional oxygen. So in this example, we've got a sodium and chlorine as elements, and those are the only things present. And that ide basically says that's all that's there. Now, we might have something like sodium nitrogen and chlorine. Now, sodium once again is closest to the top left, then nitrogen, then chlorine. So this one would simply be chloride. They usually don't go any further than 2, but really in the simplest terms, if you've got a compound that's got sodium, nitrogen and chlorine, you would simply put the element that's furthest from the top left at the end, and if there's no oxygen, you would cap it with an ide. So that ide means these things are only present and there is no oxygen there that we need to worry about. Okay, so now we're going to deal with something a little bit more complex, and we're going to get to see why naming in chemistry is, as much as it is a science, it's also an art, and you'll get to grips with when to call something by what name. It will take years of practice to get used to this, and it is really just a case of talking about it lots and lots, and you'll pick up the nomenclature as really a background task in your head and eventually you'll become quite fluent in it. This is far more like learning a language than it is learning hard facts or a systematic method for something. It does have that language quality to it. So we've got hydrogen, sulfur, and oxygen. Now, oxygen's interesting because it's in the atmosphere and it's what a lot of things react with. So for this, we find that hydrogen is closest to the top left, followed by oxygen, then sulfur. However, we're going to deal with the oxygen slightly differently. And so this one is going to be called Now, it's worth noting that you can either use a pH or an F for sulfur. I use pH, it's just the way that I spell it. It can be sulfur with an F if you want to spell it that way. It is the same thing. There's no need to worry about that. Now, to note down that we've got oxygen, I'm not able to use ide. What I'm going to use is 8. So, hydrogen sulfate is this molecule here. And it's this molecule here because this states that we have oxygen present. Now, we will be doing acids and alkalis at some point. This is also called sulfuric acid. Now, I'm usually going to call it sulfuric acid, not hydrogen sulfate. And we can talk a little bit about why that is, but it's mainly because this name here tells me how I'm using it, why I'm using it. I'm going to be using it as an acid usually. This name does not denote that as obviously. And so this one is going to be used more often than this name here. So that's a wee example of how this is correct, this is also correct. And depending on what you're being asked, you could use both names or just one of the names. Now, the next one that I want to show you is this one here. Now, how am I going to say within the name that I've got less oxygen than this? So I can do that by saying that this molecule here is hydrogen, sulf, and I do still have oxygen, so I don't want to use ide, but there's a different number of oxygens in this molecule here, so I can say that by saying ite, which means when oxygen is present but with fewer atoms. So I've still got oxygen, but I've got less of them, and that's what that ite means. It's really the same molecule almost, but it's got less oxygens. So 8, we've got oxygen present. Ite, we've got oxygen present, but it's less than the 8. And that is about as complicated as it's going to get at National 5 for these. We usually don't even see this. This we usually don't see, but it is in the data booklet. It can come up in terms of your ability to understand things, so it's worth us just going over it. Okay, so the first task is to find out the ratio of ions using the valency for rubidium carbide, barium oxide, calcium sulfide, sodium iodide, and lithium argonide. Now, there is a asterisk at the last one, and that is a problem-solving task more than anything else. You need to think carefully about what the answer to that one is actually going to be, because it's not going to be anything similar to the other ones. This is not something that they will ask you. However, they do tend to like problem-solving questions and to chuck in things that are going to make you think a little bit in the exam. So this is a good way of thinking through how you might be able to answer that question, and what you would write down for it. It is not going to be a ratio, it is going to be a sentence. Okay, just to help you out with the last task, being further to the left overrides being closer to the top. So if you've got something that's closer to the top, you put that secondarily to it being further to the left. For example, hafnium is closer to the left but is further from the top than silicon. But because hafnium's closer to the left, it takes precedence in being put to the front of the name, because being closer to the left takes precedence over being closer to the top. Right, those are the two tasks. You can do those tomorrow and post them up on Teams. I'm already about 10 minutes late on finishing this video, so I've not actually edited it yet. By the time this goes up, it'll probably be about 9 o'clock, close to that anyway. Do the tasks on Tuesday. The next lesson video will be up on Wednesday. Hopefully that was clear. If there's any questions, please post them up on Teams. I can't enable comments on YouTube, so any questions, plop them up on Teams. That would be fab. Right, ladies and gents, have a good day.